everyone, my name is Tahereh and I'm an application scientist at Qblox and I'm focusing on superconducting qubit technologies. In this talk, I will explain to you how we can support superconducting qubits with our technology. At Qblox, we are focusing on the control stack, which is the hardware and software interface between the user who provides the algorithm and the qubit device. The company started in 2018 and it is a spun out from QTech, one of the most prestigious quantum institute. And since then, we grew successfully and we are now around 100 employees. We have global reach from Europe to US to Canada to Asia and to Australia. Our mission is to enable useful quantum computing by providing state-of-the-art and scalable control electronics. Our technology is what we call qubit agnostic. It means that it can seamlessly provide solutions for different qubit technologies, including superconducting qubits, semiconductor spin qubits, and optically addressable qubits. In the past 2 decades, there has been substantial efforts towards making useful quantum computing that can actually perform useful computational tasks. Along this path, different technologies have been emerged, but also they face different challenges in terms of coherence time, scalability, and error rate. Superconducting qubits were among the most promising approach that allows long lifetime and scalable solutions. Our control stacks support users in this field that want to work with superconducting qubits on a few qubits and the users who want to scale up the system to many number of qubits. We have modular approach so the users in the field can tailor the solution according to their needs. We have modules with analog input and output. We also have qubit time tagging modules with digital input and output. In this slide, I want to focus on the modules that are most appropriate for superconducting qubits. We have baseband control modules that provides frequency range from DC to 400 MHz to apply flux biasing for superconducting qubits. We also have RF modules that provides fully integrated solutions for both control and readout of superconducting qubits up to 18.5 GHz. We recently launched new RF socket-based modules that can perform both control and readout on the superconducting qubits from 200 MHz to 10 GHz. This module offers scalable solution and is ready to scale your system towards many number of qubits. All the modules will be then placed inside the Qblox mainframe. Once the modules are being placed inside the mainframe, they are being supported by the proprietary embedded protocols. The sync protocol synchronizes all the channels within one mainframe and within different mainframes, and the jitter is only a few picosecond. The link protocol distributes the measurement results for feedback operations with a very low latency of less than 400 nanoseconds. Before explaining how we can configure our system for superconducting qubits, I want to give an overview of how we actually operate the superconducting qubits. In this schematic, you see a typical setup for a transform qubits, where we send microwave signals to the qubit drive line to drive the qubits and to perform single qubit gate operation. By precisely tuning the phase of the signals, we can rotate the qubit around the Bloch sphere. We send microwave signals to the qubit readout feed line, and by analyzing the transmission signals, we can find the state of the qubits. If the qubits are flux tunable, we also have a flux line where we can send flux pulses to precisely tune the frequency of the qubits. And if we have more than one qubit, we can also tune the coupling strength between different qubits to perform entanglement operation. To configure the modules for this setup, we connect our RF control modules to the qubit drive line. We connect our RF readout modules to the input and output of the readout feed line, and we connect our baseband modules to the flux lines. Up to now, I only explained to you how easily you can configure your setup. But more than that, it is important to do all these operations with high precision to also achieve high fidelity. And in the following slide, I will explain to you how we can achieve this operation with high fidelity. For the control, we would like to have precise and tailored pulses. Our system allows to perform parameterized pulse operation to generate pulses in a very efficient way. Users can shape the pulses in real time and change the pulse parameters, including the amplitude, the offset, the frequency, and phase of the modulations on the fly. The pulse envelopes can be generated on the time scale of 1 nanosecond, and the pulse parameters can be updated on 4 nanosecond time scale. Other than that, it is very important to have high quality signal. For that, we pay a lot of attention to the analog excellence. Our system allows to obtain at least 50 dBm SFDR, meaning that we can achieve a very good signal to noise ratio, and it also guarantees a great phase stability over a long period of time. On the readout side, apart from the analog excellence, we also have a capability of multiplexing. This allows to optimize the number of the cabling by connecting more than one qubit to the same readout feed line. We also have the capability of onboard data processing. For instance, you can perform on-the-fly averaging to optimize the data transfer latency. The fast scalable feedback operation allows to quickly react on the qubit measurement results to perform feedback operation, including the state discrimination and conditional playback. In addition, we can also do active reset, and more in the future, it also enables error correction. Our control modules in the baseband domain for flux biasing and to perform, for instance, 2-qubit gate operation has integrated digital pre-distortion correction filter. This filter ensures that the signal reaches your qubit as intended after traversing through cables and electrical components. It also has record low 1/f noise and also minimal temperature drift. Together with a high voltage output of the order of 5 volt peak to peak, it ensures bias-free operation, meaning that through every individual channel, we can provide stable DC offset together with FPGA-based real-time flux pulsing. Now going back to our newly launched module that is called QRC. This module has higher channel density. It provides 6 analog output and 2 analog input. It is RF SOC and is completely calibration free. It provides a signal of frequency range of 200 MHz to 10 GHz. One module can support up to 5 fixed frequency qubits. If the qubits are flux tunable, we would need to add baseband modules to support the flux lines. Here I would like to give another practical example of distance 3 surface code with 17 superconducting qubits, which is one of the most promising techniques for implementing error correction algorithm. This is how our setup will look like to support enough number of the channels for controlling and reading out of all the individual qubits and to perform also operations on coupled qubits. Qblox hardware allows fully parallelized operation with crosstalk suppression that allows to implement any complicated error correction algorithm at high speed with minimized error. Our modular approach allows to seamlessly scale up your system to many number of the qubits. One mainframe, if it is fully occupied, can support up to 80 microwave channels, and it can also support up to 80 baseband channels. And by stacking many of these cluster mainframes, we can seamlessly scale up to thousands of qubits. On the software side, the hardware is controlled by Python interface. For the low-level software control, we have the Qblox instruments that allow users to write Q1, which is the assembly language. Qblox instrument can also act as API layer for integration into user software platform. For high-level control, we have Quantify software package that simplifies quantum experiments by having rich library of quantum operations for different qubit technologies, by having analysis classes and visualization tool. It allows hybrid gate and pulse control. It is Python-based and open source, easily accessible to everyone. Users can also connect to Qiskit and run any Qiskit experiments on our hardware. With Quantify, we have already many notebooks available for superconducting qubits, including complete single qubit gate calibration, and also we have notebook available for coupled qubit characterization, including 2-qubit CZ gate calibration and conditional oscillation, among other available notebooks. So user can easily use those notebooks to start working with Quantify. I come to the conclusion of my talk, and in summary, we have a complete solution for superconducting qubits. We provide ultra-fast and high-precision control and readout of the superconducting qubits. The software is very user-friendly, and the system is ready for scaling up to many number of qubits. Thank you for listening to this talk, and if you want to find more about Qblox technology, please check our website at www.qblox.com.